In this video, we will be talking about lever and particularly the principle of lever. So lever is one of the type of a simple machine which we use in our day-to-day life in many places. Like most of the things that we use is basically works on the principle of lever. Even in our body as well, our bones, our joints works on the principle of lever. So what is this lever? According to the principle of a lever, the turning effect of the effort at the fulcrum should be equal to the turning effect of the load at the fulcrum, which means eventually is this formula. Your effort is effort multiplies with effort arm is equals to the load multiplies with load arm. That is what it means. So what is this effort arm, load and load arm? So effort is the force that we are applying onto the lever. Load is the object moving that you are seeing because of the what you can say force that we are applying. So the work that has been done by the lever is basically seen in how the object is moving. Okay, and the distance between the load and the fulcrum is the load arm. The distance between the effort and the fulcrum is the effort arm. And this whole rod is actually your lever. And that's how you can understand the whole role of the lever. Like however or whatever the amount of force that you are putting it, that you will see the same on the other side as well, like how the object is going up and down. Okay, just like a seesaw, if I can say. Okay, so this is the formula. Effort times effort arm is equals to load times load arm. And with that also, since you're talking about a simple machine, you need to calculate the mechanical advantage. So the mechanical advantage is load over effort, or load is divided by effort. Okay, where whatever the load that you are seeing as in terms of the work done by the machine is divided by the effort, the force that you are putting it. So for a lever also we can say that mechanical advantage can be equal to the effort arm divided by load arm, since in lever you can actually see the presence of effort arm and the load arm as well. So this is the principle of a lever in terms of theoretical manner, and in the formula as well, calculative manner also. You can understand the lever, principle of lever. Now we will talk about the different types of a lever based on the positioning of the what you can say load, effort and fulcrum. You can divide the lever into three classes. So here we are going to see the first class lever. So in this first class of lever, what you can say is the fulcrum of a lever lies between the load and the effort. It is somewhere in between, and this is what you can say is a first class lever. Okay, so generally in this case, in the first class lever, your effort arm is taken longer than the load arm. So it is not perfectly between, as I said, it is like somewhere in between. And in that case, your effort arm is always longer and your load arm is always shorter, which basically ensures the greater mechanical advantage. Means we made it like that so that you can actually utilize it for a greater mechanical advantage. And for that, the example that we can take here is a beam balance, I'm sorry, a seesaw, a pair of scissors, a handle of a hand pump, a pair of pliers, a claw hammer or a crowbar. All these examples are the first class ones. Like in the seesaw, if you look at closely, the one end is always been longer, which is like you can consider it as a effort arm. Like whoever is pushing it means applying the force will always be having a longer arm, like from the very beginning. It's not like, so if you see a perfect seesaw, it will be like that. Right now, what we see in the playground is like balanced, where both can play with each other. So that is why the load arm and the effort arm has to be equal. Okay, but in terms of pair of scissors, you can see the same thing. Like you can see the ends of the scissor are little bit longer. Like this part is very longer comparatively to the part which is there here, like on the efforts part. So effort is always shorter, and your cutting part is always longer. Same with the hand pump also. Your the pump that you are basically pushing and pulling is always longer comparatively to the actual like this pump that is putting there. So the hand that this hand movable thing which you can say here, like this part is actually longer. Same with the beam balance also, it works like that. So you see the position of the fulcrum, see the position of load and the effort, and you can actually say that this is first class lever. Similarly, you have the second class lever, where again you have to see the positioning of the fulcrum. So when the load on a lever lie between the fulcrum and the effort, now the fulcrum came at the very end and load comes in between. Okay, so this is what you can say is a second class lever. In this second class lever, the load arm is always shorter than the effort arm, because again you can see the load came in between, somewhere in between, and effort is always at the very end, and you calculate the effort arm and the load arm between the load and fulcrum and the effort and fulcrum. So that is why if it is the end, your effort arm will always be longer. So the mechanical advantage of the second class lever is always greater than one, because your effort arm is always greater. The force that you are putting will always be greater than the load that you are moving. Okay, because it works like that. It has been made like that, I can say. So here you can see the example of a wheelbarrow, a nutcracker, a mango cutter, or the oar of a boat, a stapler, a door, and a bottle opener. All of these examples works on the same principle. So your fulcrum is at very end, as you know, okay, which is in this case you can see here, in this case you can see here, in this case you can see here. Like the movable part. Always remember, fulcrum is your movable part from where your lever or this rod can move. Okay, and the effort is at the very end in all the cases, as you can see, and the load comes somewhere in between, which is basically you can see how you're moving that load. So in the nutcracker you can actually see that how the nut is being broken, sorry, because of the effort that you are putting it. Same with the bottle opener, also same with the wheelbarrow. You are basically taking this whole load that is in this wheelbarrow so that you can move it easily. So in all of these examples, you can see the utilization of second class level. And lastly, we have the third class level. Now in this case, what will happen is the effort applied on a lever lies between the fulcrum and the load. That is a third class level. In the first case, the fulcrum is in between. In the second case, the load is in between. In the third case, the effort comes in between. Okay, so in this case what you can see here is effort arm again will be shorter. So for whatever have applied the theories on the second level, second class level, the same I will apply here as well, just opposite, because now the effort comes in between. So your load arm will always be bigger, your effort arm will always be shorter. Okay, so in a third class level, the effort arm is always smaller than the load arm. Hence, the mechanical advantage of the third class lever is always less than one, because whatever the amount you are putting in, okay, it will always be lesser because your load arm is so bigger, so you will lose a lot of amount of loss. But in some places, you need such kind of things as well, because it will give you some kind of efficiency. But as I said, these kind of levers can actually increase the speed. They can't give you the more amount, or it won't multiply your force, which is in the case of second class lever, but they will 100% increase your speed, because you will have a lot of area, I can say, in order to cover with the help of the load. Okay, so with this, the examples would be sugar tongs, forceps, fire tongs, fishing rods, spades, human forearms, and knives and the brooms. All of these examples works on the principle of third class lever, where you can see the fulcrum at the very end, the load at the very end, and the effort somewhere comes in between. Like wherever you are picking these sugar tongs or the forceps or the fire tongs, you're picking somewhere in between. Okay, and then you're picking the load from the very end, and your movable part is at the other end. Same with this spade also. And you can see human arm also works on the same principle. Your effort is in your muscles. Okay, your load is in your hands when you are trying to lift up something, and your fulcrum is again somewhere at the one end. So whenever you are what you can say uh, pulling something, or whenever you are picking something, you can actually utilize in the third class lever. So this is like different classes of lever, and with this simple activity you can understand the lever, which is to compare the weight of two persons. That is our aim. We simply make a seesaw, and in order to do that, you can simply go to a park or your school playground also. You can sit on a seesaw with your friend and on the opposite side and note the position of the fulcrum, load, and that. Very simple. This is your fulcrum. Let's say if you are moving it, then this is your position of effort and this is the position of load. You can simply balance your friend and then load the load arm and the effort arm, which is this is your load arm, this is your effort arm, and estimate who is heavier. I mean, whoever is going down will be heavier, obviously. And you can actually calculate the weight as well. Not the exact amount, but you can find out whoever is heavier. And with this activity, simple activity, you can understand the weight, whoever is heavier, and utilize the principle of lever as well. I hope this will be helpful for you. Thank you.